we're going to take a look at another proof for a property of parallelograms, and this one is that the opposite angles are congruent. So the statement is that if a quadrilateral is a parallelogram, then the opposite angles are congruent. Okay. So this is another proof with parallelograms that we're going to take a problem and turn it into something that if we don't know how to solve it, into something that we can solve. And there's several different ways I could go about this. And what might be the most straightforward for many of us is to break this up into triangles and talk about it that way. And I could do that, and I could, prove two of these triangles congruent, so then like their corresponding parts are congruent. Or if I even want to make it a little bit shorter, I could have two triangles that I don't know are congruent, but I could use the third angles theorem. Or I could even make it a little bit faster than that still, and that is just going to be using my parallel lines. So that's my goal, is to make this as easy on myself as possible. And so I'm not actually going to break this up into triangles, but I could if I wanted to. So let's see. All I'm given is that ABCD is a parallelogram. And I'm going to, just like before, only prove one of these pairs, because whatever I do, I could just repeat the process for the other pair of angles. So I'm just going to prove that B and D are going to be congruent. So angle B is congruent to angle D. That seems like that'll be enough. I'll just call it a day there. Okay, so let's see what this looks like. So without giving too much away, I'm just going to start this proof how you might expect, which is to number one, use my given. ABCD is a parallelogram. That's given to me. And then, since I haven't drawn anything out, or drawn anything in, added it to this parallelogram, I can really only use my definition at this point. This is the only thing I have available to me. So I will say that AB, segment AB, is parallel to segment CD. And the reason for that is my definition of a parallelogram. A quadrilateral is a parallelogram if and only if the opposite sides are parallel. And that comes from 1. And so then I'm going to do the exact same thing with my other pair of sides, AD and BC. AD is parallel to BC, and I'll use the exact same reason. So the question is then, where am I going to go next? So if I'm not going to use triangles in this proof, I'm actually going to go back to something even older than the triangles that we've talked about, and that is just parallel lines. And so I'm going to use my parallel lines here to talk about some angles that have some relationships. So this is one of the often forgotten pairs of angles, but I'm going to use it nonetheless. This comes from 1. Okay. So what I can talk about here is, and maybe I should kind of highlight what's going on here with a different color. So I've got these parallel lines. AB is parallel to CD. And I have a transversal here, which is really just one of the other sides. And so what I do know, let's say I'm trying to prove B and D, I do know that, for example, angle D and angle A, they have, I should mark them as congruent, they have a name here. They are called consecutive interior angles. And what do I know about consecutive interior angles on parallel lines? I know that they are supplementary to each other. So what I'm going to say here I'm just going to refer to these as angle A and angle D because we're going to pretend like the blue lines aren't there. Angle A is supplementary to angle D. And the reason for that is that if two lines are parallel, then the consecutive interior angles are supplementary. So you might be asking yourself, well, how does that help us? And the answer is, well, really quick, which one did I use? A, B, and C, D, so 2. And the answer is, well, I can do this again. Let me mark another pair. So I also know that AD and BC are parallel, with the transversal being AB. So it'll be the case that angle A and angle B are consecutive interior angles as well, and so they'll also be supplementary. And so if I know that two angles are supplementary to the same angle, they're of course going to be congruent. And so I'm getting a little bit ahead of myself. Let's talk about angle A and angle B being supplementary first, but that's where I'm going with this. So angle A is also supplementary to angle B. All right, so let's see. I'm going to say, well, it's going to be the exact same thing. If two lines are parallel. Yeah, so where I'm going with this next is to talk about the congruent supplements theorem. And so I'm actually almost done with this proof once I do that. And so I didn't have to go through the whole process of proving the triangles congruent to each other. In this case, not that I drew them in, but if I wanted to draw the triangles in and prove them congruent, I don't have to go that far. And of course I could. There's always more than one way to prove these theorems. Okay, so A and B is being supplementary. I have to use AD and BC, which is 3. All right. And so now I can say that since angle B is supplementary to angle A and angle D is also supplementary to angle A, that angle B and angle D will be congruent to each other. This is not the transitive property as a reminder. It is the congruent supplements theorem. Anytime I'm linking two statements together, it doesn't always have to be the transitive property because I'm not linking them together here through congruence. So if two angles are supplementary to the same angle, then they are congruent. All right, and just like that, I am done. And so again, linking 4 and 5, again, I'm only doing this for one of the pairs of angles because I could easily repeat this whole process to show that A and C are congruent to each other. So this is just another one of the properties of parallelograms that whenever I have a parallelogram, the opposite angles will also be congruent.